Hydration of alkenes. Now, we've already seen the dehydration of alcohols to form alkenes. This is the opposite of that mechanism. This is the hydration of an alkene to form an alcohol. So let's just see a generic example of that. Now, these reactions are acid catalyzed. So let's just say we have something like this. Now, we're going to form carbocations here because we're using an acid. So therefore, Markovnikov's rules are going to apply. So let's just say we are in sulfuric acid and water. So dilute sulfuric acid. So maybe 5% or 2% sulfuric acid. So that's going to give us some hydronium. It'll be attacked by the alkene to deliver the following cation. That now is susceptible to attack by water. Now we have what's called a protonated alcohol. And now water will come back. Because remember, sulfuric acid is, it's like 5% sulfuric acid in water, for example. So it's very dilute. There's lots of water around. And the product would be something like this, which is the opposite of the dehydration mechanism. So you can go this way through the reaction, take out the water, and the reaction will go back this way. And that's the hydration of a double bond. So now, we've seen a few mechanisms that have carbocations as intermediates. And we have to remember, whenever you have a carbocation, you're setting yourself up for rearrangements if at all possible. Remember, molecules will rearrange their skeleton if they can go from high energy to low energy. So if they can throw a group across to another cation to form a different one that'll be more stable, that'll happen. So let's see an example of this. Now a little bit of acid, 50% in water. Now what you get is you don't get the expected alcohol. Instead you get this tertiary alcohol. You were thinking it was going to be a secondary alcohol, but it wasn't. Instead, it appears that a methyl group has moved over one carbon. So that's not unexpected in a carbocation creating mechanism. Let's take a look. So water, or hydronium I should say, gets attacked by the pi bond, forming this carbocation, which I think everyone will be on board with. And this secondary cation. Well, it's not very hard to imagine that this one of these three methyls here, they're all hyperconjugating to this carbocation, If you've forgotten about carbohydrate, go back to that unit and review hyperconjugation. It's no surprise then that this methyl group can move over to here and give us a new cation, which is now tertiary. Tertiary carbocations, as everyone remembers, I'm sure, are much more stable than secondary. And now the tertiary carbocation can be reacted upon with water to give us this protonated alcohol. And then deprotonate that. And you'll get the observed product, if you will. So that's how you do it. This is a rearrangement. Now, again, remember, molecules aren't thinking, they're reacting. So if you form a carbocation, the molecules don't know how they got there. They just know they're there. So they're going to react to that. And rearrangements are certainly possible when you form a carbocation.